Hi there, matriculants. In today's video, what we're going to do is we're going to review probability and counting. Right. So the way that I've structured this video is that we're going to first have a revision session, okay? And then we're going to end off the video by looking at the fundamental counting principle, okay? So in the revision session, we're going to be looking at dependent and independent events, mutually exclusive events, complementary events, and lastly, the addition rule. Okay, let's get started. We're going to first start off by talking about the difference between independent and dependent events. Okay. Right, so if we start off with just brief definitions of these two events, right? Two events A and B, right, are said to be independent of each other if the occurrence of one has no effect on the occurrence of another, right? And you've seen this definition quite a lot, right? But really what we're trying to say with this definition is that these two events, right, the probabilities don't depend on each other in any way, right? So an example of this is the probability or the chance, right? We can think about probability as just the chance of an event occurring, okay? Don't make the mistake of thinking that probability is a certainty that something will occur, right? It's just a chance that something will occur, right? Okay, so the probability or the chance that the sun will rise, okay, this is not affected in any way by which day of the week it is, right? So the probability that the sun will rise, okay, it's always 1/7, okay, because that event can happen once in 7 of the days of the week, okay? Now, there is something that you should know about independent events, right? And let's talk about that little property by using this example, okay? Right, so we said that we were looking at the probability, right, that the sun will rise and, okay, let's say for example, it's a Tuesday, right? This probability is the same as any of the other probabilities. Like for instance, if you say that the sun will rise and it's a Sunday, okay, or the sun will rise and it's a Wednesday, right? That probability stays constant at 1/7. Right? You can think about it that this event happens once in every of the 7 days of the week. Okay. Now, if we look at the individual probabilities, right? What's the probability that the sun will rise? Right? Just the probability that the sun will rise. That is equals to 100% or just 1. Okay. This certain event, we say it's certain, right? There's a 100% chance that it will occur, right? Now, what about the probability that it's a Tuesday, right? Well, a Tuesday only happens once in the 7 days of the week, right? Now, the little property that I wanted us to look at is the property of independent events. Right? So whenever two events are independent, then the probability that A will occur and, right, the probability that B will occur, right, in other words, the probability of their intersection, right, this is equals to the probability that A will occur times the probability that B will occur. Right. So now let's look at our situation and let's just look at it the left hand side versus right hand side. Okay, so left hand side, we looked at the probability that the sun will rise. This and is represented by this upside down symbol, right? So the probability that the sun will rise and it's a Tuesday, we said that that is equals to 1/7, right? Let's look at the right hand side. The probability that it's a Sunday, that the sun will rise, times the probability that it's a Tuesday, okay, this is equals to 1 times 1/7, right, which is equals to 1/7. Okay, so then you can see that the left-hand side is equals to the right-hand side, right? So this sort of like confirms, right, something that we understand intuitively, right? You just have a gut feeling for it, right? That these two events are independent, right? But mathematically, if we want to show or prove that two events are independent, or even when we are told that two events are independent, this is the little property that we have in our disposal, right, to use. Okay, and we'll see that in an example that's going to come up as well. Right. So just make sure that you jot down this little property about independent events. Okay. Right, so going back to our definition slide, right, we've now dealt with what is independent events. Okay. Let's quickly just talk about the opposite of that, right? Dependent events. Okay? On the flip side, two events A and B, right, are said to be dependent of each other if the occurrence of the one has an effect on the occurrence of the other, right? So in other words, what we're saying here is that their probabilities, right, depend on each other, okay? So the probability that event B will occur, right, depends on whether or not A has occurred, right? And vice versa, right? The probability that A will occur is dependent on whether or not B has occurred, right? So an example of this, it's quite a lengthy example, but we'll talk to it, okay? So the probability or the chance that you will be the first prize winner, okay? Just notice the condition of this probability. You want to be the first prize winner, okay? In a raffle, right, where the winner is announced last, okay, and the three winners are chosen from the same bag. This is quite a common thing that happens with a raffle, right? You guys buy tickets, they put it in all in the same bag. Somebody puts their hand in the bag, shuffles the tickets around, and then just takes out names at random, okay? And usually how this works is that the first name that they pick is going to be the third prize winner. The second name they pick is going to be the second place winner. And then the last name that they pick is going to be the first prize winner, okay? Depends on the raffle. Sometimes they only just choose once and that's the winner. That's kind of unfair, right? But over here, we're looking at the situation where you are going to be picking three winners from the same bag, right? Now, realize that the probability of you being the first prize winner, right, is actually dependent on other people winning the third and the second prize, right? So let's talk about this very quickly. So let's assume that in the raffle, right, only exactly three people entered, right? So exactly three people are in the pot, right? Obviously, that this is not going to be true, but we are going to assume that it is, right? So let's assume that in our bag, right, there's the bag, right, it's full of tickets, right, and all of these tickets have your guys' names on it, right, and the person who's going to be drawing is just going to put their hand in the bag and take out the ticket and read out your name. Right, let's assume that 17 of those tickets, right, belong to somebody called Ben. Right, 13 of those tickets belong to somebody called Mary, and 6 of them, right, belong to you, right? Now you can see that we now have a total of 36 tickets. Okay, so let's draw a tree diagram to represent this. Okay, so in the first draw, right, so the first time the person puts their hand in the bag, right, there's three different things that can occur, right? They can pick a ticket that has Ben names on it, right, meaning that Ben wins, or they can pick a ticket that's written Mary, which means that Mary wins, or unfortunately, they can pick a ticket that has your name on it, right? So what's the probability of these three events occurring? Well, Ben has a 17 out of 36 chance of winning. Mary has a 13 out of 36 chance. You have a 6 out of 36 chance. Okay. Now, what about in the second draw? Right? Draw number 2. Right? In draw number 2, okay, if they pick the tickets that says Ben, right, in the first draw, right, they can still pick a ticket that says Ben, right? But let's just say that most of the time in the raffle, right, they're not going to consider it if they pick your name again because you've already won, right? So in the second draw, they're only going to consider tickets that have the name Mary or you, okay? But now let's notice what has happened over here, okay? Because in the first draw, you've already picked one ticket, right, and one person has won, we've decreased our sample space, right? So now we don't have 36 tickets anymore. We only have 35 tickets in total, right? So Mary still has a 13 out of 35 chance to win, right? You still have 6 out of 35. Ben will still have 17 out of 35. You will still have 6 out of 35. Ben 17 out of 35, right? And Mary 13 out of 35. Okay. Now let's look at draw number 3. So in draw number 3, right, if we assume that there's only 3 people in this pot, obviously in draw number 3, right, you will have to win, okay? So you will win, right, over here, Mary has to win. So now the desired outcomes over here, right, is for you to be the first prize winner, which is this person here in the third draw, right? So the outcomes that we're looking at is Ben winning the third prize, Mary winning the second prize, and then you winning the first prize, okay? Or you can have the other way around, right? You can have these 2 people switched around. Mary can win the third prize, Ben can win the second prize, and you win the first prize, right? So that is the 2 different desired outcomes that we are looking at, right? But either way, right, you can see that the probability of you winning this first prize, right, is dependent on these other 2 people winning the third and the second prize. Okay, you can see that your probability keeps increasing, right? Right, so that is basically how you see dependent events, right? And it's actually quite simple, right? It all just comes down to this matter of replacement and without replacement. So with replacement, okay, then what you do is that case where, you know, in the textbooks when they talk about you have a bag of marbles and you pick a marble and you put it back, right? So if you put it back, right, then you keep your total sample space constant, right? So then what you really are doing is you're creating independent events. But then if you have a case like we have, right, where you have without replacement, because you can imagine in a raffle, once they've drawn somebody's name, they're not going to put it back in the bag, right? They put it aside, right? So then what they're doing is they're decreasing the sample space, right? And when the sample space decreases like this, right, then your events become dependent on each other. Right, so let's look at the following question. Okay, so this question was taken from your classroom mathematics textbook, right? You can find it between the pages 355 and 356. Okay, so it says that we have 10 red balls and 5 red balls in a bag. Okay, so this is the example that I was talking about just now. Okay. They're asking you what is the probability of drawing 1 red ball and 1 black ball, right? So in other words, they want the outcomes black then red or red then black, right? And you have to consider 2 different situations, right? The first situation is if the first ball is replaced, right? And the second situation is if the first ball is not replaced, right? So you can see over here, right, you are basically just going to be looking at the difference between independent events and dependent events. Okay. Right, so this is how we would set up this situation. Okay, let's start off with situation A, where we have replacement. Okay, so let's quickly just understand the tree diagram. Right, so the first time you put your hand in the bag and you draw a ball, right, you can pick a black ball or you can pick a red ball. Right, you have a 5 in 15 chance of picking a black ball and a 10 in 15 chance of picking a red ball, right? Now, if you put that first ball back in the bag, right, then those probabilities remain the same, okay? The second time, you can still pick a black ball or a red ball, right, and your probabilities are exactly the same as before, right? Same thing as if you pick a red ball first, the second time you can still pick a black ball or a red ball, right? So now what are our desired outcomes, right? Our desired outcome is to have black then red or red then black, okay? So basically what we're looking for is these two options over here. Okay, so black first and then red, or red first and then black. Okay, so we can conclude by saying that the probability, right, of picking a black ball, then a red ball, or, right, so or is symbolized with this upside down shape, right, this means union, right, or picking a red ball and then a black ball, right, this can occur in two ways. This is equals to the probability that you pick a black ball first, then a red ball, plus the probability that you pick a red ball and then a black ball. Right. So now, for this probability, right, this probability where you have these two outcomes, right, that is going to be given by the multiplication of the probabilities on the branches. Okay. So for black, we have 15 or 5 out of 15. And we need to multiply that with red, right, which is 10 out of 15. And then we need to add to this branch over here. Okay, so 10 out of 15 times 5 out of 15. Okay, and that works out to 4 over 9, right, which is equals to 0.4 recurring. Right, we can just write it as 4 over 9. Nice and compact. Okay. Now let's look at the flip side, right, where you now have without replacement. Okay, so after taking out this first ball, the first ball is not replaced. Okay. Now in that case, for your first try, right, your probabilities are still going to be 5 out of 15 for the black ball and 10 out of 15 for the red ball. Okay. But then if you pick a black ball first, right, then you've decreased the number of black balls that you have. You now have 4 black balls out of a total, right, sample area that has also decreased down to 14. Okay. For the red balls, you still have 10, but now out of a total of 14. Okay. If you pick a red ball first, right, the probability that you'll pick a black ball is then 5 out of 14. And if you pick a red ball first, the probability that you'll pick another red ball then becomes 9 out of 14. Okay. Again, we are still interested in these outcomes over here, black and then red, or red and then black. Okay. So let's calculate that. Probability is going to be the same calculation. Okay, and this probability works out to 10 out of 21, right, which is 0.47, right. You can see that now the probability has increased, right. The only reason why it's increased is because you've decreased your sample space, right. You've shrunk your sample space from a total of 15 to 14, right. So there's now a greater chance of these events occurring, right. So we'll just write it as a fraction, 10 out of 21. Okay, so that's the difference between looking at events where you have replacement and events where you have without replacement, right? It really just boils down to just being careful about the calculations, right? So this step over here, where you have a decrease in your sample space and sometimes also a decrease in the number of objects that you have in total. Okay. Now let's look at another example that is actually going to require you to set up a tree diagram, but it's not necessarily this type of situation where you have replacement or without replacement. Okay. So that example comes from the November 2019, right, past paper, right, and this is question number 10, right. So they say over here that the school library is open from Monday to Thursday. We have 2 students, Anna and Ben, right? Both studied in the school library one day this week. Okay, so they both studied either on a Monday, a Tuesday, Wednesday, or Thursday. Okay, Now they say if the chance of studying any of the days of the week is equally likely, right? Calculate the probability that Anna and Ben studied on the first question 10.1. We need to calculate the probability that they studied on the same day, right? And then 10.2, we need to calculate the probability that they studied on consecutive days. Okay, so consecutive means that days following each other. Okay, so this is also the type of situation where you need to set up a tree diagram in order to solve this, right? And you have to be a little bit smart about how you set up your tree diagram, because that's going to determine whether or not you're going to find success in answering this question, right? The best way that I found of setting up a tree diagram is basically to set up a first event for Anna, right? And then set up a second event for Ben, right? And then we're just going to take note, right? So I'm going to create a little key for myself, right? That M is going to represent Monday, right? T is going to represent Tuesday. W is going to represent Wednesday. And because I've already used T, I'll use TH to represent Thursday. Okay, so now we know that from the question they told us that the probability that you study on a Monday is the same as the probability that you study on a Tuesday, which is the same as the probability that you study on a Wednesday, or the probability that you study on a Thursday. Okay, and since we have 1, 2, 3, 4 days over here, we can take it that it's a 1 out of 4 of those days. Okay, so you're going to study, well, they even told us they studied 1, right, out of these 4 days this week, but then the library is only open from Monday to Thursday, so the week is basically consisting out of 4 days. Okay, so let's just construct our tree diagram quickly. Right, so for 10.1, we're looking for the probability that they'll study on the same day. Okay, so we can go over to our outcomes, right, and just note what you're saying, right? That's going to help you to figure out what's going to come on this other side, right? If you want them to study on the same day, right, then you're looking for the desired outcomes where they both study on a Monday, right? Or they can both study on a Tuesday. Or they can both study on a Wednesday. Or they can both study on a Thursday. Right? So notice that every time when we're looking at this, we always said or, right? And or, according to the rules of counting, mean that you have to add those probabilities, right? So the probability that they will study on the same day is going to be the probability that they both study on a Monday, or, right, which we can actually replace with just because we want to do a calculation. So plus, right, the probability that they both study on a Tuesday, plus the probability that they both study on a Wednesday, plus the probability that they both study on a Thursday. Okay, and this works out to be still 1 over 4, right? Or you can write this as a decimal if you want to, 0.25, right? So there's a 25% chance, right, that Anna and Ben, right, will study on exactly the same day. Now let's calculate the probability that they will study on consecutive days, right? So this one you have to be a little bit careful about, right? So the probability that they will study on consecutive days. So let's start off by just focusing on Anna. If Anna studies on a Monday, right, then the consecutive day to a Monday is a Tuesday, right? So then we have to take this outcome over here, right? If Anna studies on a Tuesday, right, then the consecutive day to that is a Wednesday, right? So we're looking at this outcome over here, Tuesday, then Wednesday, right? If she studies on a Wednesday, then Ben has to study on a Thursday. Now it's going to flip, right? If Anna studied studies on a Thursday, right, then the consecutive day to that is going to have to be the day previous to that, because the school library closes on a Thursday, right? So if Anna studies on a Thursday, right, and remember that Anna is this first letter over here, right, then Ben has to study on the Wednesday, right? So we're looking at this outcome. Anna over here is studying on a Monday, and then Ben is studying on a Tuesday, right? But what about the reverse of that? What if Ben studied on a Monday, right? So Ben studying on a Monday, and then Anna studying on a Tuesday, right? So that's this outcome over here, right? So we've dealt with the reverse of that. So these two go together, okay? What about the reverse of this, right? So Anna studied on a Tuesday, Ben studied on the Wednesday. But what if Anna studied on the Wednesday and Ben studied on the Tuesday? That's going to be this outcome. Right, so these two go together, okay? And we've already dealt with this one, right? So the opposite of these, so these two go together. Right, so Anna studying on a Wednesday and then Ben studying on a Thursday, or the opposite way around, right? Or the other way around. Anna studying on a Thursday, Ben studying on the Wednesday. Okay. So then we have all of our outcomes, right? So we're going to have, so now each of these probabilities, right, are just 1 over 4 times 1 over 4, right, which is just 1 over 4 squared, right? And then we're going to have plus 1 over 4 squared for that one, plus 1 over 4 squared for this one, plus 1 over 4 squared for that one, plus 1 over 4 squared, plus 1 over 4 squared. Okay. So then we have, let's see, 1, 2, 3, 4, 5, 6 outcomes, 2, 4, 6, 1, 2, 3, 4, 5, 6. Okay, right. So then this is going to simplify to 6, right, times 1 over 4 squared, right, which is just equals to 6 times 1 over 16. Okay, let's see. Okay, so if we simplify this, right, 2 goes into 6 3 times, right, and 2 goes into 16 8 times, right. So there's an 8 out of 16 chance was that Anna and Ben will study on consecutive days, right. Okay, so now we're going to move on to talking about mutually exclusive events, right. So when we talk about mutually exclusive events, we're basically talking about those events where the intersection of the two events is 0. Okay, so we're going to jump straight into a question, right? And again, this question is taken from your classroom mathematics textbook, right? So we are told that A and B are mutually exclusive events, right? So it's given to us that these two events are mutually exclusive, right? So which means that we know that the intersection of these two events, right, so the probability of A and B at the same time is equals to 0, right? They tell us that the probability of A or B occurring is equals to 0.8, and the probability of B complement, right, that's what that little symbol over there, right, that just means the complement or not B, right? So the probability of not B is equals to 0.3, right? We need to then calculate the probability of A, right? This is just going to be algebra. Let's now look at the probability of B occurring, right? So the probability that B will occur, right, is equals to 1 minus the probability that B does not occur, right, or the complement of B, okay? So then 1 minus 0.3, that is equals to 0.7. Okay, so that's the probability that B will occur. Right, so now the probability that A or B will occur, right, if the two events are mutually exclusive, okay, that is just going to be equal to the probability that A occurs by itself plus the probability that B occurs by itself. Right. Usually we would have over here minus the probability that A and B occur, but since A and B is equal to 0, we can cut that equation right over here. Okay. So this part or this equation is only valid if the two events are mutually exclusive. Okay, so I just made a quick note over here, right? Let us not confuse this property, right, for mutually exclusive events with what we've spoken about previously about independent events, right? So for independent events, we talk about the intersection of those events being the probability of A times the probability of B, right? When we talk about mutually exclusive events, the union of those events, right, so the probability that A or B will occur, right, so that's equal to the probability that A occurs only plus the probability that B occurs only. That's actually also just the definition of mutually exclusive events, right? If two events are mutually exclusive, then it's either A occurs or B occurs, right? Those two events can occur at exactly the same time, okay? So we are given that this probability is 0.8, right? We want to calculate the probability that A will occur. We've already calculated that the probability of B occurring is 0.7, and we did that by using the complement of B, right? So then 0.8 minus 0.7 gives us that the probability of A occurring has to be 0.1, right? So now that we've talking about independent events again, right, let's look at another past exam paper, right. This is again taken from the November 2019 paper, right, and this is the first part of question 11, right. So over here they say that event A and B are independent, right. So we are told that these two events are independent of each other, right. Then you're given the individual probabilities of these two events occurring alone, right. So the probability of A only is 0.4 and the probability of B only is 0.25. Okay? The first question wants us to represent the given information on a Venn diagram, right? And also indicate on the Venn diagram the probabilities associated with each region. Okay? Then the second part wants us to determine the probability that A or not B will occur. Right, so let's go. So for 11.1.1, we need to just draw a Venn diagram. Okay, so there's our sample space. Okay, there is event A, and there is event B. Okay, so these two events are independent, right? So we just spoke about that the probability of A and B, right? So the intersection, if the two events are independent, is then going to be given by the probability of A times the probability of B. Okay, so that's 0.4 times 0.25. Okay, that works out to be 0.1, right? So 0.1. Okay, so now this value is what's going to go inside over here, right? Now, it means that the probability of B only, right, is going to be 0.3, right? The complete or the total probability of A occurring is 0.4, right? And then the probability of B only is going to be 0.15. So now you can see that 0.4 plus 0.25, okay, that doesn't give you a total probability of 1, right? So which means that we have some probability in the sample space. So we're just going to have 1 minus this answer. Okay, so the probability that the event just falls in the sample space, so neither A and B, is 0.35. Okay, so 0.35 is going to go in there. Okay, so that's the first question done, right? We've now drawn a Venn diagram and we've indicated all the probabilities associated with each region. Okay, now 11.1.2, right? We're now looking for the probability that A or not B will occur. Alright, So this one might sound a bit tricky, but just remember that all just means everything, okay? And I told you so far in the video multiple times, you've heard me say that all, right, according to the rules of counting, means that you need to add, okay? So we're just going to go on our Venn diagram and then we're going to find the appropriate regions, right? So we want A, right? So we want the region A, okay? So A can occur, right? That's A, right? But then we want not B to occur, right? So now the regions not B are these regions over here. If you're in the sample space, then you are not B, right? And also if you're in this little circle, right, this part over here, then you are also not B, you are A only, right? So it's either you're in the sample space or you are in not B, right? So this part here for A only, right? Then A only is also not B, okay? So now we want the union of these, so we just need to add all these probabilities, right? So we're going to have 0.3 plus 0.1 plus 0.35. Okay, so that's going to be equals to 0.4 plus 0.35, which is 0.75. Okay. Right, so now we can carry on to talking about complementary events, right? Okay, so events are complementary, right, if they are mutually exclusive, right? So as I said, complementary events are not a new event, right? If two events are mutually exclusive, then they are automatically complementary, right? Okay, and the way that we denote that two events are complementary, right, is by placing this little dash after the event's name, right? So something like a dash, right? This is read as the complement of event A, right? Now, you need to know that for complementary events, we've already seen this in one of the problems that we did. The probability of A plus the probability of B is equals to 1, right? This is quite easy to remember, right? So basically what we're saying is that there's a 100% chance that either A will occur or B will occur, right? Right, so this problem, right, again, has been taken from your classroom mathematics textbook, right, and we are asked what is the probability of throwing at least 1/6, right, in 12 rows of a die, right. So what's happening here is that you're taking a die, right, and you're going to roll it 12 times, right. So now you want to calculate what is the probability of throwing at least 1/6. Okay, so the easiest way to solve this problem, right, is to notice the fact that you actually have mutually exclusive events here, right? The first event, right, which you can consider event A, right, is the event that you get a 6, right? The second event, right, is the event that you don't get a 6. Now, because they're mutually exclusive, they are automatically complementary events. Okay, so then we can use the the property of complementary events to calculate this probability. The probability that you throw at least 1/6, right, is going to be 1 minus, right, the probability that you don't get a 6 at all, right, so not a 6. Okay, so now this is going to be 1 minus, well, on a die we have the numbers 1 to 6, right? So if it's not a 6, right, there's 5 options that are not 6 out of the 6 total options, right? And you're going to throw this die 12 times. Okay, so you can just raise this to the exponent of 12. Okay, you can even do this with a tree diagram, right? And you'll see that when you multiply the arms, right, you're going to end up having this multiplied with each other, right, 12 times. Okay, so then we are then going to have 1, well, let's just solve this on a calculator. Right, so this works out to be 0.89, right. Okay, so you have a 0.89 or 89% chance, right, of throwing at least 1/6, right, in 12 rolls of a die. Okay, the addition rule, right. And this is true for any two events, right? Okay, so the probability that A or B will occur, right, is equal to the probability that A will occur plus the probability that B will occur minus the probability that A and B will occur, right? So again, this is taken from classroom mathematics, right? And they say over here that the probability that a student chosen at random, right, at a school plays soccer is 0.35, right? The probability that a student at the school walks to school is 0.52. The probability that a randomly chosen student plays soccer and also walks to school is 0.27. What is the probability that a randomly chosen student plays soccer or walks to school or does both? Right. Okay, so really the most difficult thing about this question is just getting all the information out of this paragraph, right? So we have that the probability that a student chosen at random, right, at the school plays soccer, right? So let's just create a key. S is soccer. W is going to be the fact that the student walks to school. Okay, so what we have is that the probability that the student at the school plays soccer is equal to 0.35. The probability that the student at the school walks right to school, that is 0.52. The probability that a randomly chosen student plays soccer and also walks to school, right, so the probability that you play soccer and you walk to school, that is 0.27, right. We want what is the probability that a randomly chosen student plays soccer or walks to school, right, so plays soccer or walks to school. And basically this or also just includes this event over here where you actually do both of those things. Okay, so the probability that you play soccer or you walk to school, right? That's the question, right? So you can see that this is going to be a straight application of just the addition rule. Okay, and that you can also look at it on a Venn diagram, right? So we have that the student plays soccer or they walk, right? Or they walk, okay? So if you want the probability that they play soccer or they walk, right, then you're looking at these two events. Okay, so it's either they play soccer or they walk to school or they do both of those things, right? And now because of that intersection, right, we've actually double counted that intersection, right? So you can actually even write down the addition rule just simply by looking at the Venn diagram, okay? The probability that you play soccer or you walk is equal to the probability that you play soccer plus the probability that you walk minus one of these intersections, so the probability that you play soccer and you walk to school, right? So then you just substitute 0.35 plus 0.52 minus 0.27. Okay, and this simply just works out to 0.6, right? So there's a 60% chance that you play soccer or you walk to school or you do both of those things. Right, so now we've reached the concepts that we're going to deal with in grade 12, right? And that is the concept of the fundamental counting principle, right? Let's look at what it says. Right, so the fundamental counting principle is just a way that we use, right, in order to manage a series of choices, right, which are made in order for an event to occur, right. So we are still within the realm of probability, but now this is a little area where the event that has to happen is made up of a series of choices, okay. So the fundamental counting principle simply just states that when you're given these series of choices, right, then the total number of ways that that event can occur, right, is simply given by the product of those choices, right. So you can see over here we have N times M times O, right, where N, M, and O are your respective choices. Okay, and let's look at this example, right? Take, for example, a furniture store, right? So in this furniture store, they want to do a table display, right? So like what is shown in this picture, right? They want to display the table that they sell, and they just want to put nice things on the table, right? And usually the things that they put on the table is also things that they sell in the store, right? It's a way of merchandising, okay? So all of these items, right, which they're going to, oh, sorry, I missed something, okay. So at a furniture store, a table display has to be created using a carpet, a pot plant, and a stack of books, right. So all of which are items which are sold in the store, right. Richard is the person who's responsible of this task, right, and he has 3 different carpets currently available, right, so you can see them over there. Right, there's 5 different pot plants that he can choose from, and there's 2 different stacks of books that he can use or he can combine, right? Now the question is, in how many different ways, right, can the table display be put together, right? So that is just going to be an application of the fundamental counting principle, right? The different ways that this event can occur, right, which is the event of creating this table display, right, is going to be given by the product of these choices, right? Of course, he's going to decide on one of the displays, right? But we are going to calculate his total number of ways of creating this table display. Okay. Okay, so to answer this question, right, the total number of ways that the table display can be put together, right, that is going to be given by, well, he has 3 carpets to choose from, times, right, the 5 different pot plants that he can choose from, times the 2 different stacks of books that he can put together, right? So we have 5 times 2, right, which is 10, right, and 10 times 3 is 30, right? So the table display can be put together in 30 different ways. Right. So something else that occurs, right, when we are looking at the fundamental counting principle, right, is that we are sometimes going to need to use the permutation formula, right? And now to permute, okay, so this word to permute, right? When you permute, it means that you pick with order, right? So what this means is that you are very picky about the order in which you are picking these things, right? So let me make an example for you, right? So let's say you have a red square, right? You have a blue square, and you have a green square. Okay. So if you're going to permute, right, these objects, right, these 3 objects, right, it means that you're going to pick them with order, right? So for you, it's going to matter, right, which one comes first, which one comes second, and so on, right? So the first order that you can create is where you pick the red square first, right? So you're very picky, you like, I'm going to stick with the red square first, right? So that, which means that the second square that I'm going to put, right, can either be the blue square, or you can put the blue square number last. Then which means that you have this position to put your green square and that position. Right, so that's the one set of options, right? In this option you have green, red, blue, right? And in this one you have blue, red, green, right? So these 2 different options, right, count as they count as different things, okay? So when we're permuting, these options count as 2 different options, okay? It it matters the fact that the blue came first and then the red and then the green, or the green came first and then the red and then the blue, right? So the number of ways that we can arrange three, right, objects, right, where these three objects are distinct, like we can see over here, right, is equals to 1, 2, 3, 4, 5, 6, right? So you have 6 ways of arranging three distinct objects. Okay, and that is also given by the fundamental counting principle, right? So if you use the fundamental counting principle, then basically what we say is that all of these represent three different positions that we can fill, right? And in this first position, right, so that's the first position, right, you saw that we had three different choices, right? We could either put the red square first, or the green square first, or the blue square first, so right, so we had three different, these are choices, right? What about the second position, right? In the second position, right, we only had two choices left, right? So it's either we put the blue and then the green, or the green or the red, or the red and the green, right? So we only had two choices, right? And this last position was just the remaining square, right? So it was just one choice over here. Okay, now the fundamental counting principle says that when we have choices like this, right, then you just need to multiply, and 3 times 2 times 1 will still give you these 6 different ways. Okay. Okay, so we saw how you could permute three different objects, right, or three distinct objects using the fundamental counting principle, right? But sometimes we're going to need to actually apply the permutation formula, right? And the permutation formula allows us, right, to calculate the number of ways that you can permute our things, right, from a group of n given things, right? So basically what we're doing here is that we have a group of things, right, and we only want to create arrangements from a certain amount of those things, right? So if we look at this example that we now have, right, say you have 5 different tiles, right? So now you have 5 distinct tiles, right? And you want to know in how many ways can you permute only 3 of them, right? One way to do it is the manual way, right, which is to draw out all of the different possibilities that you can have, right? And really, the only difficult thing here is just to be able to arrange your thought process, right? So you can see that there's one group where you can have the tiles starting with the red tile, right? And then you're going to have a rearrangement of the other ones, right? Or you can have the opposite of that, where you end with the red tiles, right? And that is true for all your different situations, okay? So if we use the manual route, right, to calculate how many ways can we permute 3 items, right, from 5 items, right, 5 distinct items, it's very important that these items have to be distinct, okay? Then using the fundamental counting principle, we know that that's just going to be equals to the product of our choices, okay? And over here we have 2 different choices that we can make, right? The first choice that we can make is which group we are in, right? So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different groups, right? So that's 10 choices, right? So by groups, I mean that it's either you're in the group where you start with the red, or you start with the green, or you start with the blue, or you start with the black or the orange, right? Or with the opposite groups, you end with the red, you end with the green, you end with the blue, you end with the black, or you end with the orange, right? So that's your different choices in terms of your groups, right? Now, within each of these groups, you have 6 different permutations, right, or arrangements, right? So 1, 2, 3, 4, 5, 6, right? So if you times that by 6, right? So the number of ways that you can permute 3 items, right, from a group of 5 ends up being 10 times 6, which is 60 ways. Right, so that's a long way of calculating that, right? The short way is just for us to use this formula, right? So NPR just means picking our items from n distinct objects, right? So for our case, we have 5, pick 3, right? So that's going to be equals to, just substituting into the formula, right, you're going to have 5 factorial divided by 5 minus 3 factorial, right, which is going to be equal to 5 times 4 times 3 times 2 times 1, right, which this is just the number of ways that you can arrange these 5 different items, right, if you didn't want to pick any of them, right, that is just the number of ways that you can arrange these 5 different tiles, right, 5 times 4 times 3 times 2 times 1, okay, then divide that by, well, you still have to compute what's inside of it here, right, you still have to deal with what's inside of it here, okay. So 5 minus 3 is 2, right? And then 2 factorial is just 2 times 1, right? So that ends up being 5 times 4 times 3, because this 2 times 1 cancels out, right? And if you work this out, right, this still works out to 60 different ways, right? And you can see all the different ways here on screen, right? Right, so now let's go back to our furniture shop, right? So at the furniture shop, a display, right, of the available pot plants has to be created on the main window, right? So one on a hanging shelf and one on the table, right, in that specific order, right? There are 5 different pot plants which are available, right? So in how many different ways can the display be created? Well, in the number of ways that we saw when we used those 5 different squares, right? This is exactly the same problem, okay? We're still just applying this permutation formula, right? We have 5 different pot plants, right? We want to permute, right? Actually, this time we only want to permute 2 of them, okay? Because one of them has to be hanging and the other one has to be on the table. So then, substituting into the formula, we now have 5 factorial divided by 5 minus 2 factorial, right, which simplifies to 5 factorial divided by 3 factorial this time, which is going to be 5 times 4 times 3 times 2 times 1. All of this divided by 3 times 2 times 1, okay? The 3 times 2 times 1 cancels out, leaving us with 5 times 4, which means that we can now create this display in 20 different ways. Okay, so when you're dealing with questions, right, in the fundamental counting principles section, right, one of the situations that can occur is permutations of indistinct objects, right? So now this word permutation just means arrangements, right? And we already spoke about the fact that the word permute means to pick with order, right? So you are very much concerned about the order in which you pick the things, right? Now, the number of ways that you can permute indistinct objects, right, you should already know or seen from before, right, when you were permuting those 3 different tiles or those 5 different tiles, right, whenever you have to permute indistinct objects, and the key here is that your objects are distinct, right, in other words, they are different from each other, right, there's no similar objects, right, the number of ways that you can permute indistinct objects is always in factorial, right. So an example of this is if they ask you how many ways can the letters of the word format be arranged, right? If you look at the word format, right, each letter, right, so you have F, you have O, you have R, you have M, you have A, you have T. Each of them only show up once, right? So you have one F, one O, one R, one M, one A, one T. Okay? So because each of them show up only once, then you have this type of permutation, right? So the permutation of indistinct objects, right? So the number of ways that you can arrange these letters is going to be given by, well, there's 1, 2, 3, 4, 5, 6 of these letters. So then you can arrange them in 6 factorial ways. Right, and then we never leave a factorial like this, we always evaluate it. So you must grab your calculator, right, and write the answer for this. So you're going to go 6, right, and you have to go shift factorial, right, that equals to 720 different arrangements. Right, so that's the one type of permutation that you can have, the permutation of n distinct objects. Another type of permutation that you can have is the permutation of similar objects, right? So whenever you have objects where some of them are the same, right? And this is always going to occur with the situation of arranging letters, right? Now you can see that in evergreen you have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters in total, right? So if you just arrange these 9 letters, right, and assuming that all of these letters were distinct, right, so in other words, these E's was E1, E2, E3, and E4, right, so if you assume that they are distinct, right, then you just go back to the problem that we just did, right, the number of ways that you can arrange n distinct objects is just n factorial, which in this case is going to be 9 factorial, right, but unfortunately, right, these letters are not distinct, right? So what we do is we divide out the arrangement of those similar letters. Okay, so you have 1, 2, 3, 4 of your E's, which are similar, right? But you also have, I'm concentrating on these E's, okay? But I can see now that we also have an R, right, which is repeated, right? So we have an R there and an R there. So we still have to divide this by 2 factorial, right? Then we have an N and we have a G and we have a V. Okay. So this represents, this is equals to the number of ways, or we can actually say the total number of ways, to arrange the letters. Okay. So now sometimes these permutation questions can be mixed with probability. Okay. So now we're going to be considering the letters of evergreen again, right? Question A, we want to find out what is the probability that a randomly chosen arrangement, right, will start and end with the letter E. So we have 9 different positions to fill, right? What we want to do is we want to fix the start and the ending position, right? So we want to put an E over here and fix it, and we want to put an E over here and we want to fix it, right? So we can't change those two, right? What we can do is play around with the arrangements here in the middle, right? So first of all, you can assume that these letters are going to be distinct, so you now only have 9 minus 2, you now only have 7 factorial, right, arrangements here in the middle, right? But out of those 7 letters, well, we already used 2 of the E's, right, but we still have 2 of these E's which are similar to each other, and we still have the 2 R's which are similar to each other. Okay, that gives you 1,260 arrangements. Okay, but we're not done, right? What we were asked for here is the probability, right? So this is the number of ways, right, or the arrangements that we can do if we start with an E and end with an E, right? We're now going to need the total arrangements that we can do with these 9 letters. Okay, so the total arrangements that we can have is 7,560, right? So then therefore, the probability that the word will start and end with E is going to be that divided by your sample space. Okay, and it works out to, it simplifies down to 1/6. Okay. B, what is the probability that a randomly chosen arrangement does not start or end with the letter E? Okay, so now this is going to be mutually exclusive events, right? So it's either you start or end with the letter E, which is like we calculated above, or you don't start or end with the letter E, right? So the probability, right, of not starting or ending with E is going to be equals to 1 minus the probability that it does start and end with E. Okay, so we have 1 minus 1 over 6. This is 6 over 6, so this is just 5 over 6. That's question C, right? What is the probability that a randomly chosen arrangement will not have the e's in consecutive order, right? And by consecutive order, we mean that they're not going to be next to each other, right? So with these problems where you don't want things to be next to each other, it's easier to just think of them being next to each other, right? So we are now going to consider the number of arrangements where these e's, right, are actually next to each other, okay? So this is sort of like arranging a group of people, right, where you want a certain group, right, to sit next to each other. Okay, so which means that the positions, okay, that these 8 letters can take is a total of 1, 2, 3, 4, 5, 6. Okay, so 6 positions. Okay. Now within these positions, right, they can obviously rearrange, right, but then they are similar to each other, so it's going to be 4 factorial divided by 4 factorial, which is 1. Okay. So then I'm just going to have to consider the remaining arrangements. Okay, now the way that I consider the remaining arrangements is that I consider just one of these cases. Right, so if you consider case A, for the remaining letters, if they are distinct, right, I know that within these remaining letters I still have these sneaky R's, right, these R's are very sneaky. Right, but first of all, if I just forget about the fact that those R's are similar, right, and I just think of the fact that they are distinct, then I have 1, 2, 3, 4, 5 positions, right, then I just need to divide out that similarity, which is 2 factorial, right. Okay, that's going to be given by the positions that they're going to fill, right, so the 6 positions, right, times the arrangements, which is 5 factorial over 2 factorial. Okay, so that gives me 360, right? So now, if I want the opposite of this, right, so if they are not together, right, so then the total arrangements, okay, where they are not next to each other, is going to be given by all the arrangements, all the possible arrangements. Okay, so 7, 5, 60, right, minus the fact that they are next to each other, the arrangements where they are next to each other. That's going to give us 7,200. The probability that this will occur, right, so then it's this, right, so the fact that they are not next to each other divided by our total arrangement, 7,560. Which is 20 divided by 21 or 0.95, right? So there's a very big chance, right, that the arrangements will not have the e's in consecutive order. Okay. Right, so now for today's final question, right, we are going to look at the second part of the November 2019 paper. Right, so over here they say that Motors Incorporated manufactures 5 different body styles, right, 4 different interior colors and 6 different interior colors as indicated in the table below, right. So you have 5 body styles, right, then from those 5 body styles you can get 4 interior colors, then from those 4 interior colors you can get 6 exterior colors, right. So they say that the interior color of the car must not, right, the interior color of the car must not be the same as the interior color. Alright. Motors Incorporated wants to display one of each possible variation of its cars on the showroom. The showroom has a floor space of 500 meters squared, right? And each car requires a floor space of 5 meters squared. Okay? Is this display possible? Justify your answer with the necessary calculations. Right, so now in order for us to make a car, right, in this company, right, we need to choose a body color, an interior color, and an exterior color, right? So you can see the fundamental content principle coming through, right? These are our 3 different choices, okay? But because of this restriction over here, where the interior color of the car must not be the same as the interior color, we're going to have to split this up into a few cases, right? So the first case that I identified, right, is the case where you pick a blue interior color, right? Let's see what happens, right? You can pick the 5 body styles, that's fine, okay? But then for the interior color, if you want to fix that to be blue, right, then you can't, because of this restriction, pick blue again, right? So blue for the exterior color gets cancelled, right? So you only have one choice for your interior color, right? But now your exterior color decreases down from 6 to only 5 choices, right? So you have 5 different variations of the cars which specifically have a blue interior, right? Another case similar to that is picking a red interior, right? You still have your 5 body shapes, that's fine, right? But then if you decide to then pick a red interior, right, then you can't pick red as your exterior color, right? So again, you only have 5 choices for your exterior color, which gives you 25 again, okay? Now let's move on to case number 3, right? So case number 3 is going to be neither picking a red or a blue interior, right? So we're going to pick the 5 body shapes, and then we're not going to pick the red interior, right, or the blue interior, because we've already done that, right? So which means that we're only left with 2 choices in terms of our interior color, right? Now our interior color is gray or black, right? So which means that we can pick any one of these exterior colors, because gray or black does not repeat, okay? So which means that for your exterior colors, you have all of these 6 options available to you, right? And that gives us a total of 60 variations of your cars, right? So in total, Mass Incorporated has 25 plus 25 plus 60, right, which is equals to 110 cars, or 100 different variations of its cars that it has to display on the showroom, right? Now we were told that each car takes 5 meters squared of space, right? So 5 times these total amount of cars, right, will give you 550 meters squared of space which is needed, right? Now their showroom is only a floor space of 500 meters squared. So then therefore we can then conclude that it is therefore not possible to display all the possible variations of the cars on their specific showroom. Okay, so they don't have enough space. Alright, so that brings us to the end of today's video, matriculants. I hope that you enjoyed this quick run through of dealing with probability and also the fundamental counting principle. Until next time, guys. Bye!